Okay, the atmospheres of stars create absorption spectra. Explain how absorption or dark line spectra are created and how scientists use them. Okay, so this is the continuous spectrum, right? Why is there a continuous spectrum? Well, this is just black body radiation, okay? We studied this last year, right? The power coming out of a star is, what is it? It's the emissivity, Stefan Boltzmann constant, area. I think it's temperature to the fourth, right? I think we got everything there, right? Okay. Um, and remember that the individual particles on the surface of a star are super chaotic, right? So they're not all going the same speed, so therefore they're not emitting all the same frequency. There's this black body radiation spectrum, kind of a thing, right? And that's what we're seeing here, right? There's going to be a peak where it's the brightest, like this thing's peaking maybe here, right? And then, the blue stuff is going to be here, and the reddish stuff tails off like that, okay? So we've got a continuous spectrum. This is the emission lines of a particular element, okay? So you can see that it emits these photons, right? But remember that for every emission of a photon, you can also absorb that same exact frequency, okay? So as soon as they discovered these emission lines, they also noticed that the spectra of stars had these dark lines, and the dark lines appear at the exact same spot that the bright lines appear, right? So this is when the element is emitting radiation. This is what happens when you shine a light, when you shine this light, this continuous light, through that same gas, whatever this is, right? You shine through that same gas, and what it does is that gas then absorbs those particular lines, right? Now, it also will emit those lines, but it doesn't emit them necessarily in the same direction. And so you don't get them all. It absorbs those, and you don't see them, okay? So this is absorbing. So how are they formed? Well, part of the picture, right? It absorbs those particular frequencies and emits them possibly in a different direction, okay? So this is what you need to know, right? Is that stars have an atmosphere, okay? So when I say the star itself, this is plasma, okay? This is a super hot, fiery material, right? It's not fire as in oxygen fire, but it's a nuclear fusion, okay? And the radiation from it, this continuous spectrum, is radiating outward. But before it can get into space, it has to go through the atmosphere of the star, right? And in passing through the atmosphere, these particular frequencies or wavelengths are absorbed. Okay, so this is what we see from a distance. We see this, right? Only it's far more complicated than that, right? Okay. Now, what's interesting is that the element helium, for example, okay, literally means like a heliostat is something that makes the sun sit still, right? So helios, that word means the sun, right, or something like that, right? The Greek root of that is sun. Right? So helium literally means sun element. And basically they saw the absorption spectrum of helium in the sun before they discovered helium on Earth, which I think is just super cool, right? The scientists knew that this was a different element because they looked at all these absorption lines, and they only saw it in the sun. So they're like, it's the sun element, right? Okay. But here's the cool thing is that the atmospheres of stars contain a mixture of different gases in different proportions and also at different temperatures, okay? And so what we can tell from the absorption spectrum of a star, we can tell its temperature, okay? If we can tell its temperature, we also know its size and therefore its brightness, okay? We can get its intrinsic brightness in watts per square meter, or sorry, watts, right? And then we can we can actually, we know how bright it actually is, right? So that we can look at these absorption spectra and we can say, hey, that's a 100-watt light bulb. Well, that one's a 400-watt light bulb. That one's only a 25-watt light bulb. This one's a 1-watt light bulb. Okay, we know exactly how much power that star puts out. Okay, and therefore we know how bright it is. If we know how bright it is and how bright it appears, we know how far away it is. So there's all kinds of things that scientists do with this. But that's sort of the main thing, is that we can tell the temperature and the composition of the star. But another interesting thing too is that we can tell how many heavier elements there are in the star. Stars that were created earlier in the universe are poor in heavier elements because they weren't created yet. And stars that were created later in the universe's life, right? The universe is 13.7 billion years old or something like that, right? Okay. Later stars that were born later in the life of the universe, have more heavy elements because there's more of them around to form the star, right? All kinds of things. You know what else you can tell? How do we use them? If the star is moving away from us, these absorption lines shift to a longer wavelength because it stretches them out. It's the Doppler effect. It's a little different with light. Like, you have to use a different formula for it, but it's the Doppler effect. So you can measure the star's relative velocity to you. Boy, there's just so much you can do. And if you listen to this whole video, you should just pat yourself on the back.